Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. And I'm on chapter 9, which is on dynamical systems and chaos. And this is my fourth lesson on section 9.1, which is on discrete dynamical systems. Today I'm going to talk about decimal expansions, which I'm sure you guys all learned in grade school when you learn long division, though you probably didn't learn it as a dynamical system, but that's what it is. So anyway, let's begin. So I'm defining this dynamical system here, where we start. Remember, every dynamical system you start with a seed. That's just a starting value. So we're going to start with a seed 0 comma x, where x is an arbitrary real number. And the way we're going to let this system evolve is the first element of our sequence is going to be a decimal digit. In other words, a number from 0 to 9, non-negative integer from 0 to 9. That's what we're calling D. And alpha is just going to be some real number. That's actually going to be our remainder, it turns out, when we're doing the long division. But then what we do is once we have D comma alpha, we replace that with the floor of 10 alpha. Floor just means the smallest or the largest integer that's less than or equal to that number. So just the largest integer that's less than 10 alpha. And I think you guys can see that's always a non-negative integer from 0 to 9, no matter what alpha is, as long as alpha is less than or equal to 1. Yeah, I guess alpha has to be less than or equal to 1 in order for this to work, because it's a remainder upon division. And then that's the digit that you get. And then the remainder is just going to be 10 alpha minus the floor of 10 alpha. I think you remember that's what you do when you do long division. You always subtract the digit, and then you have a remainder, but then you multiply by 10 and subtract the last digit. That's what you did when you did long division. So anyway, that's how this system works, and we're gonna look at some examples. So yeah, I'm actually just gonna give you one example here. We want to find. Here's what the problem says. We want to find all attractor sets. Remember, attractor sets are the sets where it keeps either it's a fixed point where the dynamical system ends up at a fixed point, or it could be it oscillates, which means it ends up at a cycle. And in this case, it turns out our attractor sets are going to be cycles. We're going to get 2 cycles. But here's what the problem's asking for. We're starting. So we want to find all attractor sets where every element is of a form. The seed is a form 0 comma n over 13. So those are the seeds we're starting with. All right, actually, we're going to start with 1/13. Yeah, and then if you do it one iteration, I think you can see that when you multiply, the rule is that you multiply our alpha naught, if you like, is 1/13, and our initial d naught is 0, and then we're multiplying, the alpha by 10, we get 10/13. That's still less than 1. So when we take the floor of that, we're going to get 0. So our first digit after decimal point is 0. And then we again multiply alpha by 10, but we take the 4. So we get 100 over 13, which is 91 over 13 plus 9 over 13. 91 over 13 is 7. That means the second decimal digit is 7, and we're left with a remainder of 9/13. I'm not going to go through all the steps in detail here. You guys can do this yourself. But this is what you would do if you did long division on 1/13. You get 0.076923. Repeating. And this is the repeating cycle. And if you combine the digits with the remainders, you get the subtractor set. The first element is 0 comma 10/13. Second element is 7 comma 9/13. Third element is 6 comma 12/13. Then you get 9 comma 3/13, 2 comma 4/13, and 3 comma 1/13. Remember, we started with 1/13. And so that's going to give us, again, when we started with 0, comma 10, 13. So I think you can see this goes into a cycle. And this is the attractor set. Yeah, not all. I think you guys all remember when you did long division of rational numbers. Sometimes they repeat just at the very beginning, but sometimes they have a pre-period first. And this is kind of typical for dynamical systems. You usually have a pre-period, and then it starts repeating after some time. This one doesn't have a pre-period. It starts repeating right at the beginning. But this is just one of the two attractor sets. You actually get another one if you start with your seed is now 2/13, 0, comma 2/13. If you multiply 2/13 by 10, you get 20/13. That's 1 plus 7/13. So now your first digit is going to be 1. And then, you can do all the math. I'll just do one more step. So you multiply 7/13 by 10. That gives you 70 over 13, which is 65 over 13 plus 5 over 13. 65 over 13 is 5. That means the next decimal digit is 5, and then you have a remainder of 5/13. I'm not going to go through all the steps here, but once again, you get a cycle of length 6. So you can end up getting 2 cycles of length 6, and your second cycle is this one, 1, comma 7/13, 5, comma 5/13, 3, comma 11/13, 8, comma 6/13, 4, comma um, what is that? Can't read that one. 8/13, I think. And then 6, comma 2/13. 2/13 was what we started with. So then we're going to get a repetition. So I think you kind of see how that works. So this particular example with a denominator of 13th gives you exactly 2 cycles of length 6. Those are the attractor sets for this dynamical system. And I just want to say one more thing about all this. There are certain special type of prime numbers known as cyclic primes. Notice that the denominator I used here, 13, is a prime number. It's not a cyclic prime because we get 2 cycles of length 6 if we do the long division. But for special types of prime known as cyclic primes, you always get just 1 cycle of length p minus 1. And the smallest cyclic prime is 7. I think I talked about cyclic primes in chapter 3. You guys probably remember the decimal expansion of 1/7. This is 0.142857 repeating. 142,857 as an example was known as a cyclic number, where it's a pretty amazing number because you multiply by any number up to 6 and you get a cyclic permutation of its digits. It actually turns out you get cyclic permutations of the digits of 153,846 if you multiply by the right multiples, not all the multiples up to 13, but some of them. And the same for 76,923. So those are not cyclic numbers, but 142,857 is with the cyclic prime 7. That's just the smallest example. I think the next one is 19, if I'm not mistaken. And I don't remember what the cycle is. But anyway, this is an example of a dynamical system. I think it's kind of an interesting one. And that completes my video for today on decimal expansions as a discrete dynamical system. So thank you for watching. Long live math, and I'll see you guys next time. Bye.